Thank you very much for the invitation and the opportunity to lecture in Lisbon. It's always a great pleasure to be in Portugal. For me, I've been in Portugal many times, but each time enjoyed it very much. Different places, in particular in Lisbon. And Thank you. So the topic of my lecture today is definitely a topic in differential geometry, which is the scalar curvature attached to a Riemannian metric. And so this lecture is really dedicated to some recent, but also not so recent development about the scalar curvature of Riemannian manifolds. A priori, it's a very weak invariant, and you believe you cannot do much with it, but actually, this is not true. It actually, a lot is hidden in the scalar curvature. And what has been really remarkable is that the topic has really undergone a number of transformations and has remained active until very recently. And I want to recall the attention to two recent documents, one which you can even watch it because it's online, by Misha Gromov, who gave 4 lectures on scalar curvature in 2019. And there's also a long text attached to it. And even more recently, Misha has produced another 200-something pages on the topic. I asked him a question, he said, no, just wait a little bit. And next week, he just sent me this 200 pages paper. That's the way Gromov is functioning. Anyway, and another one, which is something I've been reading extensively recently, which is some kind of a global survey by Stefan Stolz, who has been one of the important contributors, as I will explain, on recent developments, which appeared in an archive in 2022. So you see it's very much recent. And the title is Positive Scalar Curvature, Constructions and Obstructions. Anyway, so that's the topic. So the summary is the following one. I want to explain general consideration of scalar curvature, then to explain why positive scalar curvature is different from negative scalar curvature, which should not be. The first time you think about it, you don't see any difference between the two. Remind you of the fact that in the Kählerian setting, I will define what the Kählerian setting is, scalar curvature plays a very specific role. I will also propose to you something which I personally contributed to, which I think has not been explored completely, and I'm trying to come back to it. Well, one conjecture I couldn't prove, but maybe it's a wrong conjecture. So that's the role of conjecture, sometimes to force you to find things, and I will then come to remarks. So the general consideration of the scalar curvature is the following one. Of course, as you know, the first time the concept of curvature was discovered was in the Discusiones sobre las superficies curvas de Carl Friedrich Gauss, 1827. Clearly, he had understood this almost 30 or 35 years before, but as you know, Gauss waited to really have explicit formulas, and he was not happy with an abstract approach to it. So why is this important? So if you take a hypersurface, of course, the notion of curvature was present through the extrinsic curvatures. So in particular, the principal curvatures, which played a very important role. And then one thing Gauss discovered is, which is fundamental in his essay, is the fact that if you take the product of the two principal curvatures, actually, you can access it strictly by looking at things on the surface. That is, it's not an extrinsic quantity, depending on the embedding. It's an intrinsic quantity strictly connected to the geometry of the surface as a surface. So it was, of course, a very important discovery in 2 dimensions, on surfaces. And then, as you know, the generalization of the usual theory of surfaces, which was a major one, was the so-called Habilitationsvortrag Vorlesung of Bernhard Riemann, 1854. assumptions on which geometry is based, in which he wants to consider more generally on space with the local coordinates, xi, quantities which are scalar products whose coefficients depend on the coordinates. Actually, such expression existed already. You can express the Euclidean metric in polar coordinates, for example, and then you have a variable coefficient. But there you want just fully generally look at this such an expression. And then in the paper by Riemann, there is only one formula which explains in which way these new geometries are different from Euclidean geometry. And he introduces a quantity which looks like a complicated quantity, which is called the Riemann curvature tensor, which is a 4 tensor, so it's quite a complicated object, which measures the deviation from Riemannian geometry, from Euclidean geometry. So it means that if you are in Euclidean space, even in general coordinates, if you compute this curvature tensor, you find 0. So that's Riemann Euclidean space is flat, has no curvature. And it's interesting because it's not clear how he came about to find this. I mean, it's not explained in the text. And the only place where you see some calculation related to this is in a submission that Riemann made to the French Academy of Science, in which you see some calculation which probably led him to the curvature. And at that time, he was interested in how would heat propagate in an inhomogeneous medium. That was what he was doing. Anyway, finally, the person who really gave the most systematic approach to this was Gregorio Ricci Corbastro. In 1888, for the first time, one had the concept that I will come back to of a covariant derivative. But then, very importantly, Ricci Corbastro introduced 1904. So you see, 50 years after Riemann, a piece of the Riemann curvature tensor, which of course later on played a very, very important role, which is called the Ricci curvature, which was introduced by Ricci Corbastro, which is basically you have these 4 tensors. So these 4 tensors spontaneously is 3 times covariant, 1 time contravariant. So it means if you take the linear map, which to a vector z associates RZXY, you get a quantity depending linearly on x and linearly on y, bilinearly on x and y. And that's what is Ricci curvature. So in a sense, it's a contracted form of the Riemann curvature tensor. And of course, you can go one step further. You have a metric. So if you have a symmetric tensor, because actually the Ricci curvature is automatically symmetric because of symmetries of the curvature tensor, you can contract it using the metric. So you take a trace of it, and then you get a scalar quantity depending on the point, so a function on the manifold, which is the scalar curvature. And the local expression is given by the formula I gave you. So the upper Gij are the inverse matrix of the Gij coordinates. And then you have the second derivative of the metric with respect to the coordinates. So this is the local expression of the scalar curvature if you are given with the Gij. Okay, so this is the definition of scalar curvature. And it's interesting that several people have tried, but actually the most recent one is Michal Gromov has tried to have some kind of axiomatic characterization of the scalar curvature. So he proposes the following characterizations through a number of quantities. So here is what Gromov proposes as what should be the characterization of scalar curvature. So it is a quantity which is equivariant if you let the group of diffeomorphism acting on function and on metrics. So the scalar curvature of the image of metric by a diffeomorphism is the scalar curvature of the initial metric composed with a diffeomorphism. That's the equivariance. That's one. And then also, as you've seen, if you remember the formula I showed you, it's linear in the second order derivatives of the metric. Okay, but then there are 4 more properties that he claims characterize it. I think he missed one, as I will mention later, and forget about that. If you take 2 manifolds, if you take a metric on one and metric on the other one, and on the product manifold, you add up the 2 metrics, that the scalar curvature should be the sum of the two scalar curvatures. That's one. Then there is a scaling. If you look at the scalar curvature of a metric multiplied by a factor, positive factor, then you have the factor to the -2 times the scalar curvature. So it's some kind of homogeneity property. And then there is a volume comparison, which is to say that if I take points P1 and P2 in two manifolds, having a Riemannian metric G1, G2, and then if the scalar curvature at P1 is less than the scalar curvature of G2 at P2, then the volumes of the small balls at this point satisfy for epsilon small a volume comparison. So in a sense, it claims that the scalar curvature controls the growth of volume in some way. And then you need some normalization at some point, of course, and which is if you take the scalar curvature of the unit sphere in the three space, you find number 2. And you find, if you look for the hyperbolic plane constant sectional curvature -1, then you get -2. And as I said, there is one missing, but I won't talk about that. Actually, it will be very important for us to look back at the Riemann curvature tensor and look at its symmetries. And actually, by definition, if you look the way the curvature is defined, and maybe I should have written the definition, then maybe I write the definition of the curvature. But I should have done that in my slide, which I missed. So the curvature on vectors x, y, z, I told you it's 3 times the variant, is the derivative in direction of x of dy of z minus e covariant derivative in direction of y, covariant derivative in direction of x of z, minus e bracket xy. Okay, so this is the derivation curvature. So by construction, you see, it's pretty clear that it's skew-symmetric in x and y, because I took the commutator of the second derivative, and then I have the Lie bracket, which of course is anti-symmetric. So by definition, this anti-symmetry, which I mentioned here, is pretty clear. And but it verifies also some special properties because of the covariant derivative I've used is the one which is really attached to the Riemannian metric. So if I want to be emphatic on the dependence on the metric, so that the G there. So that's the so-called relatively Levi-Civita covariant derivative, which I think is unfair because the person who really defined it for the first time was Ricci, who was the Dr. Vater of Levi-Civita. So it should really be called the Ricci covariant derivative. And it has some properties. So one of the key properties, of course, is the fact that the Riemannian covariant derivative leaves the metric invariant. So the covariant derivative of G is 0. And so this has a consequence, which is the following one. It means that in the last, if you take the scalar product of the curvature with another vector, you get a skew symmetry there. So you have, this is directly related to the fact that the covariant derivative is metric, that is, it preserves the metric. So it shows that you have this skew symmetry there. There's another one because another condition to determine dg, and actually this is sufficient to determine the covariant derivative, is to impose that it has no torsion. And then the fact it has no torsion means you have the so-called Jacobi identity, which is this one. That is when you do a secular permutation of the XYZ, preserving the order, then automatically you get the sum of these terms is 0. And then actually it's very natural to work not with the so-called 3-1 version of the Riemann curvature tensor, that is 3 times covariant, 1 time contravariant. It's nicer to look at the completely covariant version. So you, in terms of indices, it means you lower the last index by using the metric. So then you get a 4 tensor, which is purely covariant. So this is what I call the 4-0 version of the curvature tensor. And then it's very easy to see that the consequence of C1, C2, and C0 is the fact that, C1 and C2 is the fact that you have this pair, symmetry in pairs. That if you exchange X, Y, and ZU as pairs, you don't change the value. So this is very nice because then it means that you can think of a 4-0 version of the curvature tensor as an element which is a symmetric tensor on exterior forms. You see, because you have exterior forms here, and then since you can exchange in pairs, it's an element in S2 of lambda 2 of E star, because they are covariant objects. This is very interesting. So, and all tensors which verify all these symmetries, they are called algebraic curvature tensors. So that's the space which I call R, like Riemann E. And actually, if you look at what is, so of course, clearly RE is sitting inside, I'm sorry, I should have written R of E star, sits inside S2 of lambda 2 E star. But what's left is not much. It's just the 4 forms on E star. So in a sense, the algebraic curvature tensors, they are just like the symmetric transformation on exterior 2 forms, and you're just the extra piece that you have is the 4 forms. So it's very interesting from that. In particular, it helps you to compute very simply the dimension of the space of curvature tensor, because it's very easy to compute the dimension of S2 of lambda 2 E star, and you just have to take out the 4 forms. So that's very good. Which, by the way, is a space which is of degree 3 in the dimension. So it grows, the size grows very quickly. And so the first decomposition concerns of the Ricci curvature tensor was the Ricci curvature was to separate the diagonal part from the trace-free part. So Ricci can be written as a multiple of the metric with the scalar curvature as function divided by n so that the trace is exactly SG, and plus a piece which is trace-free, which you just made everything so that you have taken the trace out. So this is for Ricci. And therefore, in order to finalize the decomposition of the curvature tensor, it's important to introduce an operation which looks very bizarre the first time you meet it, but actually is very important, which we call the Nomitsu-Kulkarni product, and which is the following one. You take 2 symmetric tensors, H and K, and you have 4 tensors and 4 vectors. And with these 2 symmetric tensors, you can build a 4 tensor by doing the following construction. So the symbol which is used is both symmetric and skew symmetric, corresponds to the game you play with the terms. So you see, you still make it skew symmetric in X, Y, and Z, U, but still symmetric in pair. So almost by construction, you made so that the product of H and K being symmetric tensors is a algebraic curvature tensor. So that's very important. And then if you look at the Riemann curvature tensor, you can split it into 3 components. A diagonal part, which is the product of G by itself with a Nomitsu-Kulkarni product, with a scalar curvature as coefficient, with a normalization, which introduces the dimension. Then the trace-free part of Ricci, and what's left is what is called the Weil curvature tensor, which is something very interesting, because if you make just a conformal change of the metric, which means you multiply it just by a function, so you don't change the angles, then automatically the W doesn't change up to a factor. So in the sense, that's why it's quite often called also the conformal curvature tensor, but also W for Weil, for Hermann Weil. And you see that the scalar curvature is just in this decomposition, the piece which appears as the one-dimensional irreducible component. So in a sense, it looks like it's a very minor part of the curvature, because it's just the most trivial part you can imagine. So this is what I wanted to say on the scalar curvature. And then what are the general questions about the scalar curvature? Well, the basic question is, if I give myself a function on the manifold, can it be the scalar curvature of a Riemannian metric? So that's the most general question you can ask. Scalar curvature is a function, you give yourself a function. Can this be the scalar curvature of a Riemannian metric? I will be talking during the whole lecture about compact manifolds, but actually it's very important to look also at the non-compact case, particularly for complete metrics. And actually it's much richer and extremely interesting, and many results have been obtained recently in that. If you're looking at surfaces, again, I'm talking about compact surfaces, then there is a very important Gauss-Bonnet theorem, which says that if you integrate the scalar curvature against the volume element determined by the metric, then you get the topological invariant. You get 2 pi times the Euler characteristic. So it means that in 2 dimensions, the scalar curvature, which of course, one thing I should have said when I presented this decomposition, when you're in 2 dimensions, it's very simple to see, you forget about everything, you only have the scalar curvature. If there is no room for the rest, you have 1 over n minus 2 appearing, so of course it doesn't make sense. If you're in 3 dimensions, actually, you don't have the Weyl tensor. You only have the 1 and 2. And as soon as you get to 4 dimensions, then you have the full composition. Sorry, I should have said that. So now, of course, when you are in a surface, because of the Gauss-Bonnet theorem, if you take the sphere, for which the Euler characteristic is 2, well, the integral of the scalar curvature has to be positive, because you should get 4 pi. And therefore, you cannot have negative scalar curvature on a metric on the sphere, because the integral will be, the volume form, of course, is a positive form, so you would have a contradiction with the Gauss-Bonnet theorem. So certainly, any metric on the sphere has at least some points where the curvature is positive. On the torus, the Euler characteristic is 0, so either you have a flat metric, that's possible, or you have a metric which takes both sides, because you need the integral to be 0, so you must positive and negative. And if you are on a surface with higher genera, that is with more than 1 hole, so the torus was 1 hole, then the scalar curvature must be negative somewhere, because the integral is going to be, the Euler characteristic is going to be negative, so the integral has to be negative. So this is the situation for surfaces. And over the years, the question of manifolds admitting metrics with positive scalar curvature has taken great importance because of the theorem of Kasdan-Warner, going back to 1975. They showed that as soon as you are in dimension at least 3, then all manifolds admit metrics with negative scalar curvature. So negative scalar curvature is not an issue for any compact manifold of dimension at least 3. We have seen for surfaces that's not the case. There can be a problem like on the sphere, well, anyway. So I want to move on and
not necessarily constant. Negative scalar curvature constant as well.
Well, I have to be careful with what I mean by negative. So whether I mean non-positive or whether I mean negative. No, I do mean negative, actually. Yeah, there's no problem. I really mean stronger than non-positive.
Negative everywhere.
Yeah, negative everywhere. Yeah, sure. That's the point. And then, well, it covers the case where you have a scalar curvature which is negative somewhere, is also covered by that. But even more stronger, you have this. And then in the article, they refer to 3 categories of manifold. That's what I'm coming to now. I'm always talking now about n larger, at least 3. So there are 3 categories. The first one is manifolds admitting a non-negative scalar curvature metric, which is positive at least at 1 point. And that's the first category. I'm giving the 3 categories at once, and then I come back to my list. Manifolds with a non-negative scalar curvature metric, but no metric with positive scalar curvature. And then the third category is manifolds who do not admit a metric with non-negative scalar curvature. So the first category means that for those, so manifolds admitting a non-negative scalar curvature metric, which is positive at least at 1 point, they establish that actually any function can be realized as the scalar curvature of a metric. So that's the point I was just making for this category, but doesn't cover all manifolds. Now, the second category, manifolds with a non-negative scalar curvature metric, but no metric with positive scalar curvature, they show that then a function is the scalar curvature of a metric on such manifold, if and only if there is a point where it is negative or it identically vanishes. Okay, that's the second category. And the last one, well, as it says, there are manifolds which do not admit a metric with non-negative scalar curvature. And then, so that was 1975. 1979, Schoen and Yao have shown that dimension less than 7, because they're using minimal surfaces. So, you know, starting with dimension 8, you may have singularities for minimal surfaces. And later on, it was improved by, in 1980, by Gromov and Lawson, using spin-oil techniques. I'm going to explain that in a minute. They proved that the torus, Tn, does not admit any metric in the positive scalar curvature. So the first, well, in the theory of Schoen and Yao, it was limited to dimension less than 7, but after that, this constraint was lifted. And so it's very interesting because it shows that the torus is, you cannot find metrics positive scalar curvature, which was, of course, one of the open questions. So I'm coming to this category, which looks like a very special category of manifolds admitting metrics with positive scalar curvature. And actually, there was a very critical remark which came out of the blue by Andrei Lichnowitz, 1963. Actually, Singer also had this in his drawer, but didn't publish it. So it's the following one, which using harmonic spinners, I'm going to explain what this is connected with positivity of the scalar curvature. So here is the following story. A spin manifold, which I will explain what it means, endowed with a metric with positive scalar curvature, non-vanishing harmonic spinners, I will explain what it is, cannot exist. And there are topological reasons why harmonic spinners must exist. So therefore, as I will explain, you will have an obstruction to the existence of positive scalar curvature. Indeed, the Atiyah-Singer index theorem, which was proved in 1963, so Lichnowitz jumped on it immediately, they showed that some spin manifolds must admit non-trivial harmonic spinners. Example given was the 4K dimensional manifolds with non-vanishing A-roof genus, which is a differential invariant. And a good example in dimension 4 are the so-called A3 surfaces, providing an obstruction to the existence of a metric with positive scalar curvature for these manifolds. Because if you put together the result by Lichnowitz and this, the consequence of the Atiyah-Singer index theorem. And actually, sometime later, more than 10 years later, Hitchin, using a much more involved Dirac operator and more involved invariants than the A-roof genus, have also showed that the non-vanishing of these invariants, KO invariants, obstruct the existence of metric with positive scalar curvature on some exotic spheres. So even on objects like the sphere, topologically very nice, but if you, an exotic sphere, the differentiable structure on it is not the usual one, then you may have, you may be in a situation where there exists no metrics of positive scalar curvature. And of course, you see that's a difference between a topological invariant and differentiable invariant, because these are normal spheres from the topological point of view, but not normal spheres from the differentiable point of view. Okay, so let me try to define all these terms. So I'm going to say a few words about spinorial geometry. So I go back to the first time spinors appeared in mathematics, which was 1913. Élie Cartan was doing a systematic classification of representation of the orthogonal Lie algebras. And then he noticed that besides all the ones that people think of, namely action on Rn or tensors on Rn, he found that there were some other unexpected representation that which were actually representation not only of SON, but actually coming from the double cover of SON. When you are in dimension that is 3, SON is not simply connected, but it just has a Z2 as a fundamental group. And then you have a group covering SON, which is spin n, same dimension, but just double cover. And then, of course, the way to construct spinners today, rather than using what Elie Cartan has done, is to do the following construction. So you start with a vector space, dimension n, and you put a metric on it, and then you create the Clifford algebra. Clifford algebra is very simple. You take the tensor algebra, you take all possible tensors on E, and then you force the relation that the square of a vector is minus its norm squared. So in a sense, you force some kind of an anti-symmetry in the object. By doing so, it's very easy to see that actually the object you build is more or less same dimension as the exterior algebra, but with a more sophisticated product, which is, of course, the Clifford product. And one thing which has been noticed very quickly, actually it was known to Cartan, is that the Clifford algebras, the ones I just built, if you look at them over the complex numbers, over the real, it's slightly more complicated, but let's stick to complex numbers. They have a twofold periodicity. So if the dimension is even, then the Clifford algebra is simple. And if it's a simple algebra, it's the endomorphism algebra of some vector space. And this vector space is a space of spinners. If the dimension is odd, the Clifford algebra is not simple, but it's almost simple. It's the sum of two simple algebras. So in a sense, you see appearing two vector spaces because there are two factors, which is the endomorphism on one and plus endomorphism on another one. They are almost the same, but not exactly the same. So these spaces, sigma E and sigma twiddle E, are the spaces of complex spinners. And their dimension, it's very easy to see. I told you the Clifford algebra, its dimension is 2 to the 2m. So since you are, in the case of n equal 2m, then you see that the endomorphism, the vector space, in order for the endomorphism to be of dimension 2 to the 2m, it means the vector space is of dimension 2m. And of course, both the sigma G and sigma twiddled G of E are both spaces of dimension 2 to the m for these two cases, 2m and 2m plus 1. And also very important, I'm not going to give you the proof of that, is the group spin n acts on the spinners. So that's also good reason to call them spinners, because they are acted upon by the spin group. Of course, we don't want to do only linear algebra, we want also, or multilinear algebra, we want to do geometry, differential geometry. So you want to know whether you can make sense of all this on the manifold. And actually, the good or bad surprise, I don't know how you take it, is that if you take a manifold at random, you will not be able to define spinners. One reason for that, there is a topologically a constraint. In order to make sense of spin and action on the manifold or a notion of spinners globally, locally you can always do it, of course, but globally, you need a certain invariant, which is a certain cohomology class, which takes its value in the H2 of the manifold coefficient in Z over 2Z, must vanish. If this doesn't vanish, you cannot make sense globally. So a typical example where this doesn't vanish is the projective space of projective plane, so dimension 2, P2C. P1C is the new sphere on which there are spinners, but P2C, you don't have the notion of spinners. And very important in order to develop the geometry is that usual constructions in Riemannian geometry, the notion of covariant derivative, the notion of curvature, they carry over to spin manifolds. So as soon as you give yourself a manifold, which is spin, admits a notion of spinner, you can always, and you give yourself a metric, then you can really do what you usually do. And the very important operator, which of course was rediscovered later by physicists, was not defined by Dirac, was in 2026, that's why it's called the Dirac operator, at the birth of really quantum mechanics. Why was it introduced by Dirac? Because he was looking for a version of the Schrödinger operator which would be invariant by transformation, which were Lorentz transformation in dimension 4 for special relativity. And he noticed that, of course, with the usual Schrödinger operator, it doesn't work because the Schrödinger operator mixes second-order part on the space and first-order part on time. So if you want to have the time and the space on the same level, you need something different. And so what he found is that the square root of the D'Alembert, which is the key second-order operator in Lorentzian geometry, and this root is the Dirac operator. So how do you do the Dirac operator? Well, you take a spinor field, so a section of the spinor bundle, so spinor depending on points, and then you do the following construction. You compute its covariant derivative in direction of EI, and you Clifford multiply by EI, and EI is just any orthogonal basis. And it is independent of the orthogonal basis you take. That's an intrinsic notion. And of course, so this is this Dirac operator, and the key formula, it is the square root of the Laplace-Beltrami operator, and I will give you a proof of that in a minute. And actually, there is a very important property which later on will play a key role for spinors, is what we call their chirality. That is, if you let the volume element act on spinors in say in even dimensions, I'm sticking to even dimension, then the action of the volume element with the proper square root of -1 power in front of it is an involution. So as for any involution acting on such a space, it means you can split the space into the +1 eigenvalue space and the -1 eigenvalue space. So it means that spinors in even dimension gives rise to half spinors, that is positive spinors and negative spinors. And very importantly, because Clifford multiplication changes by vectors, changes the chirality, it means the Dirac operator maps positive spinors to negative spinors and negative spinors to positive spinors. That's very important. And the key formula, which was discovered by Lichtenowitz, but actually later on rediscovered that Schrödinger wrote it 30 years before, which is called the Schrödinger-Lichtenowitz formula, which says the following one, what I told you, namely that the square of Dirac is like the D'Alembertian in Lorentzian geometry, or like the Laplacian in Riemannian geometry. So d squared of psi is d star d psi plus 1/4 scalar curvature times psi. So you see the only appearance of the curvature in this formula, you expect that there should be a curvature term, but the only part of the curvature which matters is the scalar curvature. And this is really a fundamental property due to representation theory. So it's because this scalar curvature is the irreducible component in this trivial representation that it appears there. Of course, this theoretical approach telling you that only the scalar curvature can appear there doesn't tell you the coefficient. What's very important about the coefficient is, in fact, it's plus 1/4. If it was minus 1/4, it would change a lot of things. Anyway, so that's the key formula. And okay, so that's what I was just told you. And so why does that matter in our context of the, so this is the now, I'm coming to harmonic spinors. So harmonic spinors are very simple. They are just spinors which are annihilated by Dirac. So d of psi is 0 if a spinor field is harmonic. And of course, when you are in even dimension, it's worth looking at harmonic spinors, harmonic half spinors, that is the positive spinors annihilated by Dirac or the negative spinors annihilated by Dirac. And then the key point is that the Atiyah-Singer index theorem tells you that the index of the restriction of Dirac to positive spinors, I could have written with negative spinors, it would just have changed the sign, is exactly the A-roof genus. So it means that if the manifold has a non-vanishing A-roof genus, then the index cannot be 0. So it means that either the kernel of D plus or the kernel of D minus is not zero. So there must exist harmonic spinors because of this topological constraint. So that's wonderful, because then you have some, if the manifold has a non-vanishing Eruv genus, there is a harmonic spinor, and then you apply the Lichtenowitz formula. So you take your harmonic spinor psi, apply the square of Dirac, you get zero because that's a harmonic spinor, and then that's zero. But on the other side, what do you have? Remember the Schrödinger-Lichtenowitz formula was D star D psi, scalar product with psi. So you just integrate by part, you get D psi squared, certainly a positive quantity, and then you get plus 1/4 scalar curvature psi squared. So you get zero equal a positive quantity plus 1/4 scalar curvature, a positive quantity. So if scalar curvature is positive, you have a contradiction. So on a compact manifold, which has a non-vanishing Eruv genus, you must have harmonic spinors, and therefore you cannot have positive scalar curvature. So that's the wonderful discovery by Lichtenowitz, who immediately jumped on it as soon as he saw the index theorem by T.R. Singer. And so this looks like anecdotal, but it is not anecdotal at all. Actually, there has been 1980, sometime later, the previous one was 1963, work by Gromov and Lawson. They showed that if you take simply connected manifolds of dimension at least 5, the answer to the question of existence of a metric with positive scalar curvature depends only on the spin Bodism class of the manifold. So it means the purely topological condition on the manifold determines whether there exists a metric with positive scalar curvature. In the same article, now not anymore for, using so-called surgery techniques in codimension 3, they prove that again, in dimension at least 5, if you take a simply connected non-spin manifold, they all admit metrics with positive scalar curvature. So this very interesting situation that if you have a non-spin manifold, it means that the Stiefel-Whitney class doesn't vanish. So a very small topological invariance not vanishing actually gives you room to create metrics with positive scalar curvature. So it shows how much the problem of finding metrics positive scalar curvature is connected to topology in this very complicated way. And actually, I mentioned Stolz already for his recent article, but one thing that he showed is that the Lichtenowitz-Hitchin obstructions actually form a complete set for simply connected spin manifolds in 1992. So it means that these topological invariants, this differentiable invariants introduced by Lichtenowitz and Hitchin really tell you the whole story about concerning the existence of metric positive scalar curvature. In dimension 4, you've seen that many of these theorems starting with dimension 5. Dimension 4, it's even more complicated because you have to take into account the so-called Seiberg-Witten invariants. I'm not going to go into that. And for non-simply connected manifolds now, there are, again, some work of Gromov and Lawson, who introduced original constructions to the existence of metric positive scalar curvature, which is connected to the structure of the fundamental group. And there have been many, many refinements given by Jonathan Rosenberg and Stefan Scholz. Later on, it continued to this day, actually. And as I said, the comprehensive 2022 report by Stolz describes where the problem stands, many results depending on the algebraic structure of the fundamental group. So it's a very subtle intertraining between algebraic properties of the fundamental group and the existence of positive scalar curvature. And in all these works, the techniques are basically either the twisted Dirac operators or metric surgery. So these are the key tools to deal with these problems. In the Keller setting, maybe I should check with the time because maybe I'm, still okay, I think. So in the Kellerian setting, there is a lot to be said. So what is the Kellerian setting? So it's interesting. So what is, I'm going to do a very quick introduction to Kählerian geometry. So you not only give yourself a metric, but you give yourself also, let's assume the manifold is complex, but the object, which will be very important, is the so-called almost complex structure, which is the multiply by I square root of -1 in each tangent space. So of course, the square of J is minus the identity, because it's an almost complex structure. And so it's a linearization of multiplication by I in local coordinates. And then when you have this G and J, you can automatically construct an omega by doing the following construction. Omega of xy is J of jxy. And by construction, if the metric is a Hermitian, automatically omega is Q symmetrical. So I started with a symmetric object G. J is this almost complex structure, and then you get omega, which is automatically Q symmetric. And then the triple G, J, omega, actually redundant. If you know two of the three, you build the third. The triple is said to be Kählerian if this exterior form, omega, is closed. Okay? And then if it's closed by Durham theorem, it determines the cohomology class, which is actually a bit peculiar because omega has the advantage because it comes from a metric to be a non-degenerate two-form. So actually it makes M omega being a symplectic manifold because omega is non-degenerate. And therefore, that's why we call the class determined by omega a Kähler class. And already in the original article by Erich Kähler in the 1930s, Erich Kähler considered the case where the class is trivial. That is where you can find a function u, so-called Kähler potential, so that omega is I dd bar of u. So it's an exact form, if you want. And when the class is non-trivial, then it's very important to actually look at what is called the space of Kähler potentials, which means all functions for which, if I fix myself an origin in the Kähler metric omega, then I can form the new Kähler metrics omega twiddle, which are omega plus I dd bar of a function. Of course, phi has to be small enough that omega twiddle remains positive. Omega was positive, I deform it, but if phi is small enough, then it will remain positive. And then there are a number of properties connected to this Kähler setting. The first one is that if you play with the Ricci curvature the same game as you played with the metric, that is, you look at Ricci jxy, you create an object, a row of xy, which in the same way as omega was Q symmetric when G was symmetric, R, the Ricci curvature, is symmetric, and rho is anti-symmetric. It's a two-form. And it's even more extraordinary that you find that this two-form omega, the Ricci form, if you want, and was already discovered by Erich Kähler, that actually it is a closed form automatically, and its cohomology class is very well identified. It's actually the first Schoen class of the tangent bundle, complex tangent bundle. So it means that in a Kähler setting, the Ricci curvature, the Ricci form, has really a topological meaning because of this constraint that is the first Schoen class. And actually, Kähler geometry has been dominated by the question of prescribing the Ricci curvature, the so-called Calabi conjecture, because there is this constraint that the cohomology class of rho omega is fixed by the topology. And therefore, in the Kählerian setting, the scalar curvature, which is the object we're interested in tonight, can also be expressed in the following way. If you multiply the volume element, which you can write as omega to the m, rather than v as volume element, multiplied by the scalar curvature is the same as the exterior product of the Ricci form by omega to the m minus 1. It's very important to have this definition, and therefore the search for Kähler-Einstein metrics, that is metrics for which the omega is a multiple the Ricci form is a multiple of omega, so-called Keller-Einstein metric, has been a very important driver in Kähler's geometry. And it's also connected to the study of constant curvature, scalar curvature metrics in Kähler metrics. And of course, very easily, you see that the first necessary condition is that the first Chern class be zero or definite positive or definite negative. And when the first Chern class is negative, it was a beautiful theorem by Aubin and Yao to show that there exists automatically a Kähler-Einstein metric. So you see again, in the negative case, things are easier. And actually, from the analytic point of view, what's behind, you can use the maximum principle there. In the case of vanishing first Chern class, it means that you have to look for metrics, Kählerian metrics, for which the Ricci curvature is identically zero. And this was solved by Yao when he solved the Calabi conjecture. And the case C1 positive became very complicated and took 20 years to clarify. And so there are so-called Fano manifolds, and there are many more obstructions which are connected to the holomorphic geometry of M. So again, you are in a situation where positive scalar curvature, even in the Kählerian case, is much more complicated than negative. That's what's it. So the first obstruction which was found by Matsushima and Nishnowitz. They showed that in the case of C1 positive, then the group of holomorphic transformation of M must be reductive as a Lie group. And therefore, if it's not reductive, then you cannot have a Kähler-Einstein metric in this case. So there are examples, and typically you take CPN and you blow up a certain number of points, you are in this situation. The group of holomorphic transformation is not reductive. And actually, Nishnowitz extended this result not only to Kähler-Einstein, but to constant scalar curvature metrics. And there is a much more subtle obstruction which has been found by Akito Futaki, which is the following one. So imagine you start with a Kähler form, omega, which has the property that its Kähler class is 2 pi C1 over M. So it means that if you take the difference between the Ricci and omega, it's an exact form. It's I d bar of a certain function. And then what Futaki has done, he looks at a certain functional, which is the following one. So it's you take a holomorphic vector field X, and the value of this linear form on the Lie algebra of holomorphic vector fields is the integral over M of the Lie derivative in direction of X of this potential phi omega, which I found before. It was measuring the difference between the Ricci form and the Kähler form. And you divide by n in factorial just for normalization. And this is an intrinsic quantity. That is, it doesn't depend on the choice of omega in the Kähler class. So it shows that if this guy is, if you want to have a Kähler-Einstein metric, you must have phi omega equals 0. So if this character is non-zero, certainly you cannot solve the equation. Okay? So the Futaki character is an obstruction to finding Kähler-Einstein metrics. And you can also define it for more generally, and anyway, you can discuss that further. So, as I said, I discussed it in the context of Kähler-Einstein, but you can also discuss it in the context of constant scalar curvature. So even in the case of Kählerian case, really discussing positive constant scalar curvature is really tricky. And it continues to be tricky. Anyway, so probably I'll skip this, which is my own contribution to, because I think it's time to close. So I wanted to show you something, but I've been too slow. So what I've been doing and what I'm not showing is you can really come up with the Futaki invariant and other invariants, which are also some of them due to Kazan-Warner in a completely different way by using at the topology of infinite dimensional spaces. So it's a very general method to build obstructions. And I build many more obstructions than Futaki invariant and Kazan-Warner. But I skipped that. So that's my own contribution, which is still, I obtained some results, but there are some more results to come, I hope. And even in conformal geometry. So anyway, I've been too slow. My concluding remarks, because it's time for me to close. So you see, I've been following different paths. I mean, I showed you that there was a very intricate mixture of differential geometry, topology, and also actually infinite dimensional analysis in some way. And typically, if you want to solve the Nirenberg problem, which is to find a metric in the conformal class which has constant curvature, then you need very subtle analytical estimates, which, for example, allows you to solve the problem on the projective space due to work of Moser and not on the sphere. Anyway, but there are also topological obstructions, as I told you. And there are a number of issues I didn't cover. I spoke only about compact manifolds. And as I told you, the theory and the most recent development with complete metrics have been fantastically interesting and subtle. So I didn't cover it at all. And also another thing which has been a recent evolution in differential geometry has been to forget about differential. That is to look at coarse geometry, as sometimes Gromov calls it, which is you forget about the regularity. You forget about the differentiability. You keep only very minimal quantity so that you have a distance, you have minimizing path, but you don't ask them to be regular or anything. And you try to make sense of curvature in that sense. You see, the definition of curvature by construction is you differentiate all the time. But actually, you can still make sense, not on the value of the curvature, but you can make sense of inequalities on the curvature. So, but you see, we were dealing with inequalities. We were looking at metric positive scalar curvature. So Gromov has been really discussing this in these 4 lectures. And also, I favored the approaches involving spinors. And I really believe that more can be obtained using spinors more cleverly in geometry. And maybe, I skipped this because it's connected to what I didn't show you. So the title of this last slide is borrowed from Gromov. So its title is Scalar Curvature, Who Are You? It is the title of one of the sections of this set of notes for the 4 lectures. I know highlight some points he makes in a conclusion. So I'm quoting Michel Gromov. What are most general geometric objects that display features similar to these of manifolds with positive or more generally bounded from below scalar curvatures? So when he says more geometric, he means forgets about differentiability. Even look at metric spaces. What do you need to request? Is there a direct link between Dirac operators, which a priori, to make sense of Dirac operators, you have to compute the derivative, and minimal varieties or in the joint appearance in the ambience of scalar curvature? Is that purely accidental, or is there a link between the two? Nobody knows. For the moment, there is no link shown. And to finish, is really more explicit. Is there a partial differential equation or something more general than differential equation? Because you want to deal with spaces which are not regular, the solutions of which would mediate between twisted harmonic spinors and minimal hypersurfaces. That would be one way of connecting to the previous question. And as I said, Gromov is especially interested in the coarse geometry of spaces with scalar curvature bounded from below, when an appropriate meaning can be given to such an expression about scalar curvature when you cannot compute derivatives. Thank you very much.